Good morning. How are you? How are you doing? Welcome again. Welcome to this exciting live stream session. I'm Professor Murad Sultan Ezouidi, and today we are going to tackle, are going to, just I'll fix my phone first. Really fix my phone. No? Yes. Okay. Ezouidi theorem to solve third degree polynomial. Okay. So, here again, the Professor Murad Sultan Ezouidi is with you. Okay, welcome my learners, professors, teachers, and colleagues to this exciting live stream. Professor Amrata is with you, and today we are going to tackle one of the most challenging mathematical problems, solving a 12-degree polynomial equation, something that traditional methods simply can't handle. We will see how my method, let's say Ezouidi theorem, allows us to find exact symbolic solution where others fail. Let's first talk about the difficulties to solve polynomial to the power n. Okay, then we can wait for me. Okay, so let's start, my professors. We'll start with the difficulties of classical methods in solving the high degree polynomial equation. While classical method in fact such as Cardano or Ferraris and Abel's theorem have long been used to solve polynomials, they face significant limitations, especially when dealing with high-degree polynomial equations beyond the fourth degree. Here are the key challenges. First of all, let's see Abel's theorem. Abel's theorem. So Abel's impossibility theorem. Abel's theorem famously states that there is no general solution for polynomials of degree 5 or higher. This means that for most polynomial equations of degree 5 and beyond, we can't express the roots in terms of radicals using a definite number of operations. The general solution for polynomials of degree 5 and higher, when expressed in terms of their coefficients, require non-algebraic functions, which is what makes them insoluble by classical algebraic means. The second lack of general formula for roots degree more than 5. For quadratic, cubic, and quarter polynomials, there are explicit formulas that provide not exact roots in fact. However, once the degree of the polynomial exceeds 4, no general formula exists for obtaining the roots in terms of simple operations on the coefficients, while there are specific methods for certain types of polynomials, example, degressive polynomials. This method in fact fails for most general high-degree cases. The Bring radical for the fifth degree polynomial equation or high is extremely complicated and does not simplify the problem sufficiently. 3. Complexity of Galois theory. Galois theory is a powerful tool, in fact, in understanding the solvability of polynomials. It tells us when a polynomial equation can be solved by radicals. However, even though Galois theory provides deep insights into the structure of polynomials, it still does not offer a sample or direct method for solving most high-degree polynomial equations, algebraically here I mean. In practice, solving high-degree polynomial equations using Galois theory can be extremely challenging, requiring complex group theory and fields extensions, which is not always practical for obtaining exact roots. Numerical approximation, or we can say error estimation. Classical method, in fact, when applied to high-degree polynomial equations, often rely on numerical approximations to estimate the roots. This can be effective, but with potential errors that may not be easily qualified. Even though these approximations, in fact, can provide good enough answers in many cases, they fail to offer exact symbolic solution, which is crucial for understanding the full structure of Holmes' roots. The main opportunity here is the failure to handle special cases. Classical methods are often ineffective for handling polynomials with special root structures or symmetries, such as complex interplay of real and imaginary roots, or roots that involve hierarchical relationship, like roots involving roots of roots. For example, when the roots include terms like fifth root of two or three, classical methods struggle to express these terms in manageable form. Inability to solve high-degree problems efficiently. As the degree of problem increases, the number of potential roots grows, and the algebraic complexity of finding these roots in fact increases exponentially. Solving 12-degree, listen my learning, solving 12-degree or higher problems using classical method involves dealing with enormous expression and complex algebraic manipulation, even with the use of computer algebra systems like CAS. The task of solving such equations symbolically becomes computationally expensive and often results in approximation instead of exact roots. Lack of insight into exact root structure. Even though classical method and Galois theory can determine the existence of certain kinds of roots of their symmetries, they often fail to offer an explicit formula that provides the roots in their exact closed form. This is particularly, this is particularly problematic or problematic in American pronunciation when you need to obtain exact roots for polynomials of higher degrees that may not follow standard patterns or contains nested radicals and complex numbers. Now, how Ezouidi theorem overcomes these challenges? You see these difficulties that we said before? Listen and see how Ezouidi's theorem overcomes these challenges. The Ezouidi theorem addresses the above difficulties by providing an explicit symbolic method for solving high-degree problems exactly, with no error of estimation, with no approximation, with no guesswork. This method does not rely on numerical approximations, but instead uses recursive and algebraic transformation to determine the exact roots. Even the polynomials of degree 12 and higher, 13, 14, 15, 16, 17, 18, the theorem takes advantage of specialized relationship and properties of the coefficient that classical methods can explore, providing a breakthrough in solving polynomials that have long been considered insolvable. So we can say that this theorem provides a solid method that helps you to solve uh, that helps you solving high degree polynomial equation and see how Ezouidi theorem offers a promising alternative. So let's start now, my colleagues. I will start now. I will share the screen with you, and let's say you will see the 12-degree polynomial equation in front of your eyes. Okay, And you will see after using the theorem of Murat-Ezouidi that the roots, the symbolic roots, are reachable. You can touch them. You can see them even. Okay. So let's start. I will share first of all the screen. Okay. So this is the screen. Okay, you can see everything. Now I will go immediately to this one. So here are the coefficients of my 12-degree polynomial equation. This is L0 for the Q is 24, L1 is 264, L2 is 1760, L3 is 7,920, L4 is 25,334, L5 is the birthday, is my birthday, 14,021,978, L6 is 167,655,480, L7 is equal to 837,897,240, L8 is equal to uh, 2,234,167,360, and mine is going to be equal to 3,351,149,664, and L10 is going to be equal to 2,680,890,240, and L11 is going to be equal to 893,625,984. Okay, this is the coefficient of my 12-degree polynomial equation. I will write my polynomial to the power 12 as that. P of x equal x raised to the power 12 minus 24x raised to the power 11 plus 264x raised to the power 10 up to 893,625,944. Okay, so this in fact is my 12-degree polynomial equation. Okay, I will color the coefficient so that you can see it. I will color now the coefficient of my 12-degree polynomial equation, and you will see that all the classical method can, let's say, solve this 12-degree polynomial equation without using Murat-Ezouidi theorem. Okay, this is a fact. Even ChatGPT or DeepSeek, both of them, they make a confession paper that they could not solve 12-degree or 9. Okay, because they don't have the method. Okay, now I'm going to color this one, the coefficient, so that it be clear in front of your eyes, and start with the Professor Murad Sultan is really solving this 12-degree polynomial equation. Here I will show you the theorem that we are going to apply. So here, this is my polynomial to the power 12. My polynomial to the power 12 can be written in its standard form, either plus L0 or minus L0. This is never changed. This changed nothing. So we can say that P of x equal x raised to the power 12 minus L0 for the q, x raised to the power 11. You can see L0 for the q, in fact, is equal to 22. Then plus L1 for the q, x raised to the power 10 minus L2 for the q, x raised to the power 9 plus L3 for the q, x raised to the power 8 minus L4, x to the power 7 plus L5, x raised to the power 6 minus L6 for the q, x5 plus L7 for the q, x raised to the power 4 minus L8 for the q, x cubed plus L9 for the q, the square of x minus L10 for the q times x plus L1, L11 for the q. This polynomial had been written in its standard form. Okay. Here is the polynomial. You see, here is my 12-degree, my original 12-degree polynomial equation. We are solving today. As you can see, it's a 12-degree equation. Traditional method would rely on numerical approximations, but we are going to approach it systematically using my theorem. First, let me point out something key, like x here in this polynomial, x equal to is a root of multiplicity 6, meaning you can write your polynomial as x raised to the x minus 2 raised to the power 6 times another polynomial. Okay, but here I'm going to use the theorem, and you will see. We'll go step by step. Okay, so I will use always the coefficient of my 12-degree polynomial equation, the coefficient of the original 12-degree polynomial equation. You can see that, in fact, this is a 12-degree polynomial equation in front of your eyes. And I'm going to dive into the structure of Mr. Murat's Ezouidi, and I'm going to put k equal 0 to obtain s minus 1. By convention, s minus 1, in fact, is equal to 1, simply because it would be equal to combination n choose 0. Okay, this is combination n choose 0. Okay, that's why here s minus 1, in fact, is equal to 1. This is s minus 1 when k equals 0. Now I'm going to proceed and use the theorem of Murat-Sultan-Ezouidi. This is the theorem. You see, this one is the theorem. This relates, let's say, the coefficient of the new 12-degree equation with the coefficient of the original 12-degree polynomial equation. The coefficient of my original 12 original is that Lk minus 1, and the coefficient of the new 12-degree polynomial equation is written in terms of Sk minus 1 of 42. What is necessary to do here is to calculate Sk minus 1 of OD2, where k ranges from 0 to n minus 1, means the n is 12, so ranges from 0 to 11. That's why I should start for s minus 1 up to s11. If you want to make extension, put this as x s subscript k, it will be k plus 1, and here k plus 1, and here k plus 1, and this one comes k. Okay, and it will be from 1 to k plus 1. Okay, if you want to ignore sk minus 1. So here we told that I will dive again into the structure and putting k equal 1 to get the value of S0. S0, this is the formula. I used the theorem of Murat-Sultan-Ezouidi, and I found that S0 always equal to 0, simply because S0 is equal to the sum of the x roots of my new 12-degree polynomial equation. Therefore, as S0 equals 0, means that x plus 1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7, that I'm going to find them into exact symbolic roots, okay, plus x8 plus x9 plus x10 plus x11 has to be equal to 0. Why? That's why, because s0 is equal to 0 according to the theorem, and this is also correct. So here I make my own substitution. I find that s0 in fact is equal to an hour. We proceed. We continue, my professors, and I'm going to dive again into the structure, and I'm focusing on the last formula, minus combination 2 choose n choose 2 times n0 42 squared plus n squared times n1. I will make substitution here, and we'll obtain this is in fact is equal to 0. We can calculate this easy. Okay, now dive again into the structure. Sk minus 1 of r equals the sum from 0 to k combination n minus r choose k minus r, n raised to the power r between parentheses, negative at 0.42 raised to the power k minus r times and r minus 1. So those who have a smart mind and those who are interested in mathematics, in solving or in mastering the solution for n-degree polynomial equation, this is your time. This is your occasion. This is your chance to understand how polynomials to the power n works, how solving n-degree polynomial equation has to be done only by finding its new n-degree polynomial equation by the theorem of Mr. Murat-Sultan-Ezouidi. Okay, here I'm going to dive into the structure and put k equal 3. I will obtain this formula. Now, what's needed exactly, my colleagues, professors, students, learners, and teachers, is go and replace. Use the formula I mean, and replace L0 with 24, L1 with 264, L2 with 100 and 1760. So after making your own calculation, you will obtain that S2 equal to 0. Okay? Means if going back to the polynomial, okay, we continue. We told that now I'm going to dive into the structure again and put k equal 4 to find S3. This is my professor the formula to get the fourth coefficient of the new 12-degree equation. Just what is needed exactly. Do your best and make substitution and calculate it. So this one has to be, after making the substitution, replace a 0 with 24 and 1 with 264 and 2 with 1760 and 3 with what? With 7920. So this one is going to be equal to I. We continue. We are going to calculate the value of S4. To find S4, put k equal 5. And you will come to write the following. S4 equal combination 4 choose 1. Okay. Combination n choose 5 and 0 to q raised to the power 5 up to n raised to the power 5 times L4 raised to. So n is 12. 12 minus 4. 12 minus 4, my professors, is 8. 8. Do you see this 8? I will explain this here. So this is S4. Okay. This is combination 4 choose 1. Go to the last one. This one has to be combination 8 choose 1. Add the indices of the combination 8 plus 4 will give you the degree of your polynomial. So you structure it. Okay. So now I'm going to calculate this. So this one, in fact, is going to be equal to n. If you want to calculate this for you, I will do it now. Okay, calculation. Calculator. Okay. So here we have 4. I will make 4. Multiply by 5 choose 12. 5 choose 12. 1, 2, 3, 4, 5. 792. Multiply by 24 square. 24 raised to the power 5. I will write as, I will just put 2 times 2 raised to the power 5. Why? Simply because the 12 raised to the power 5 is a common factor. You see this 12 raised to the power 4 times 24. You can write 24 as 2 times 12. 12 times 12 raised to the power 4 is 2. 12 is 12 raised to the power 5. Also here, 24 squared is 2 squared times 12 squared. And here 12 cubed. 12 cubed times 12 squared is 12 raised to the power 5. So we can note that 12 raised to the power 5 is a common factor. Don't write it now. Okay? Now we told that minus 10 choose 3. 10 choose 3. This is 1. This is 2. This is 3. Means 120. Times 2 raised to the power 3 means times 8. Times 8. Times 264. Multiply by 264. Okay. Plus 9 choose 2. This is 1, 2. Means a plus 36. Plus 36. Multiply by 2 squared. Multiply by 2 squared. Why 2? Because I will write 24 as 12 squared times 2 squared. 12 squared times 12 cubed is 12 raised to the power 5. We told before that is a common factor. So times 2 squared means times 4 times 4. Then minus 8 times 2. 24 is 12 times 2. 12, I will put it here. 12 to the power 4 times 12 to the power 1 is 12 to the power 5 is a common factor. I'll make minus 8 times 2 means 16. 16. 16. Times 700 times 7,920 plus 25,344 plus 20,000 plus, okay, plus 20,000, just a moment, I will repeat this again. We have 4, okay, I will make 4, multiply, again, 4 multiply by 5 choose, 12 choose 5, 1, 2, 3, 4, 5, 792. Okay, times 2 raised to the power 5, meaning 32, times 3, 2. Minus 10 choose 3. 10 choose 3. Why? Because 5 minus 2 gives 3. 12 minus 2 gives 3 according to the formula. This is the formula. Okay. Times 12 times Mr. Murad minus. Okay. Okay. Minus, what is minus? This is minus. Minus 10 choose 3 is 45. Choose 3 is 120. 1, 2, 3. Minus 120. Multiply. Multiply by what? Multiply by what? Multiply by what? By 264. Multiply by 200 plus 9 choose 2. 1, 2 means plus 36 plus 3, 6. Okay. Multiply by 2 raised to the power 2 raised to the power 2 means multiply by 4. Okay. Multiply by 1000. 1760 minus 8. 8 times 2 minus 8 multiplied by 2, right? 82. Multiply by 7,920. So this one has to be equal. Okay. Minus 310, 12 squared. 12 cubed, 250, 92, 176, 98, 700, 950. Plus, plus 2, 5, 3, 4, 4. I will repeat this. Just this is what we will do. I will do it again. Look here. So this is 4. 4. Multiply by 5, 12. 4 plus 1 gives you 5. Okay. 5, 12. 1, 2, 3, 4, 5. Okay. 5, 5, 1, 2, 3, 4. Minus 462 plus 230. 792 times 792. Okay. Times 2 cubed. 2 raised to the power 5 minus times 32 minus. Maybe I didn't make it. Minus 10 choose 3. 10 choose 3. 1, 2, 3 means minus 1, 2, 0 times 8 times 8 times why 8 because 2 cubed times 264. Okay, plus, okay, 10 minus 1, 9, 3 minus 1, yes, 2, 9, minus 9, choose 2, 1, 2, 1, 2. Okay, minus, plus, we call 36, multiply by 2 squared, minus multiply by 4. Okay, minus 8, minus 8. Okay, times 2, because 24 is 12 times 2. I'll put 12 times 12 raised to the power 4 is 12 raised to the power 5. Remains only 2. So we got that. Minus 8 times 2 means 16. Minus 16. Times 7 times 7,940. Plus. Okay. Where is my number? This is my number. But later work with the adjective. Okay, I will do this. We have S4 equal. Okay, minus. This is minus 3, 12 minus 3, 10. 12 squared, 24 cubed, times L1 is 264, plus 2, 12 minus 3 is 9. Okay, 12 cubed, L0 squared, times L2. L2 is 1760. correct. Okay. Minus combination n minus 4, 12 minus 4, 8 is 1. Yes. Times 12 raised to the power 4 and 0 times 7,920. Okay. I will do it again. Okay, we have 4 times. Times 1, 2, 3, 4, 5. 700 times 792. Okay. Times 2 raised to the power 2 raised to the power 5. Yes, raised to the power 5. Okay. Then minus this 4 is positive. So minus 33, 33, 33. This is 1, 2, 3. Minus 120. Minus 120. Multiply by 8. Multiply by 264. Okay. Times 1760. This one. Now minus 1. Minus 8 multiplied by 2. Because 4 is 2 times 12. I put 12 raised to the power times 12 raised to the power 4 is 12 raised to the power 5 is a common factor in all the terms. So I'll make 8 multiplied by 2 minus, okay, all right, 8 is 8 times 2 times 7,920. So this one, you see, every time give me a number. Means that the calculator was correct. I will repeat again. We have 4. Raise everything. 4. Multiply. We told 5. Okay. Okay. 12 to 5. 1, 2, 3, 4, 5. 7, 9. Multiply by 2 raised to the power 4. Multiply again. 792 multiplied by 32 because 2 raised to the power 5 is 32. Minus. Because 10 choose 3 is 120. 1, 2, 3. Minus 120. Multiply. Multiply by 4. Multiply by 760. I will make it equal minus 8 multiply